Catch the eclipse?
I did. How about you?
Yes, I did. It was awesome.
Yeah, it's kind of neat. I hadn't realized how much I still liked it, even though it wasn't a total. The last one I went to was like 2016, 2017, something like that. That was a total eclipse, and it's still pretty cool checking it out, even with it being I think it was 80% or something like that. So I was excited.
Still pretty awesome.
Yep, yep. Anybody have any questions? Feel free to ask. I'm making up some problems right now just to get prepared. So get most people here. All right. Well, it is officially time, so I guess I should get started. Jennifer asked me about checking out the eclipse. I hope you all got a chance to see it today. Not going to have another one go over America till 2044, so we got a while. Uh, ugh, darn it. So, anybody have any questions before we get started? I like the dog, Jacob.
Thank you. Her name's Halo, by the way.
What's her name?
Halo.
Ayla. That's cool. I've got my new quote unquote puppy. Well, he's not even a year yet, so he is really a puppy, but we just got him neutered and he's still a pain in the butt. He's in the velociraptor stage. Once we get out of the velociraptor stage, it'll be a little bit more pleasant, but right now he just wants to eat us and eat the neighbor dog and eat his brother, and mostly in a playful way, not in a food way. So I guess that's good. All right. Well, I wanted to go ahead and knock out a couple other problems from this chapter 10, I believe it is. Yeah, 10. So I'm going to start off with a discrete, or actually two discrete computations of moments of inertia. I did take questions if anybody had any, but no one offered any, so I'm assuming they don't have them. So I'm going to go ahead and share my screen. Feel free to ask me questions. This is how I make all this money that I make, is by teaching you guys. So y'all definitely deserve the right to ask me questions. So by all means, please do. When this becomes available on your screen, you're going to see basically a problem. It's not unlike one of the problems that your textbook has. So I try to mimic them because your textbook author has a lot of experience and he generally knows what works year in and year out, day in and day out. So I try to make problems sort of similar to it, but not so much to be completely thieving. So anyways, in this scenario, I've got a rod that basically you can imagine, since I've got a 5 kilogram and 7 kilogram mass on the two ends, maybe the rod weighs half a kilogram. Then that's a pretty good approximation because it's a factor of 10 smaller than the lightest one. So that's not unlike maybe taking a 45-pound bar that you use for bench pressing, and if you put, for instance, 450 pounds on it, then you know that that's a small fraction of it. So that's what we're going for here, is we're just assuming that the mass holding the two masses apart has essentially negligible mass compared to the mass of the two masses on the end. And in part A, I want to calculate the moment of inertia as if it's rotating around what I drew as axis A, which is through the center of the rod. And then in part B, I want to calculate it as if it's 1 meter to the left of the 5 kilograms mass. So let's do that. So our solution is going to start off with the summation from I equals 1 to n of m sub I r sub I squared, where r sub I is the distance perpendicular from the rotation axis to mass m sub I. So part A, let's start with that one. I'm going to say I, the moment of inertia, is in fact equal to 5.00 kilograms. Now, if you notice, that's 3 meters from the rotation axis. So I'm going to put 3.00 meters and then square that. Plus, I have 7.00 kilograms. And in this case, it's also 3.00 meters away. And of course, I got to square that. The 3 squared is, of course, 9, and then 9 times 5 is 45. So this gives me 45.00 with 1 extra sig fig kilograms meters squared. And 9 times 7 gives you 63. So that should be 63.0 with 1 extra sig fig again, kilograms meters squared. So 60 and 40 make 100. 5 and 3 make 8. So this is equal to 108.00 kilogram meters squared. So that's basically the moment of inertia if I were to rotate this about the center of the 6-meter rod that's separating them. Any questions on that one? It should be pretty straightforward. The discrete's always a little easier, just sometimes just involves a little bit of math that's a pain in the butt, but other than that, it's fairly easy to do. It's just a matter of, if you have enough of them, you might have to add 15 terms or something, so that could always be a hassle. But other than that, it's not too bad. All right, I just opened up the chat window in case anybody tries to chat anything to me while I'm teaching. Looks like no one has any questions on that, so I'm going to move to part B. So in this case, you'll see that the moment of inertia is calculated about the axis that's just to the left of the 5 kilograms, and that's 1 meter away. I like using whole numbers as opposed to half and fractional meters, so that's one of the major differences between this and the version that the book does. So I'm going to write 5.00 kilograms times 1.00 meters squared. And then the other one's actually on the other side, but it really doesn't make any difference. All that matters is, since you're squaring it, is the distance away. So this one's going to be 7.00 kilograms. And of course, in this case, the axis is now 7 meters away. So it'd be 7.00 meters away. Again, I got to remember to square that. And of course, 1 squared is just 1. So this is 5.00 kilograms meters squared for that one. 7 squared, of course, is 49. And then, of course, we're actually calculating 7 cubed. 7 times 40 be what, 280? And then 7 times 9 would be 63. So that'd be 343. Zero kilograms meters squared. And just because I did that so quickly while yawning, I'm going to double check my math. Yep, 343 works pretty good. So I'll take the 343 and I'm going to add to it the 5, and that gives me 348.00 kilogram meters squared. So those are our answers. And this is like this. So anybody have any questions on that before we move on to the next problem? Okay, so the next problem we're going to do, we're going to take and let me go ahead and draw the diagram. I'm going to imagine this is my pulley, okay? And then from this pulley is a string, and on that string, we're actually going to apply a force of, let's say, 15.0 newtons. Hold downward. I'm going to say this pulley has a mass equal to 4.25 kilograms, and it has a radius r that's equal to 0.300 meters. And let's say that initially its angular velocity is 0, but its angular velocity after, let's say, 4.00 seconds, let's say that's going to be 40.0 radians per second. And what I'd like to calculate is what is I. Okay, let's also assume that it has a frictional torque on it that's going to be, let's say, 1.22 Newton meters. Okay, so there's our problem. Our solution is going to entail us knowing that the summation of the torques is equal to I times alpha. Now, with that equation, your book takes the time to, your author takes the time to tell you that this does not always work. You can't just apply this at any problem. What has to happen is this applies whenever the rotational axis of the system is not moving with respect to the actual object that's having the torque applied to it, and it's not moving with respect to an inertial coordinate system. So basically it has to be inertial, in other words. If it doesn't meet those criteria, then you only have the choice of setting the rotation axis through the center of mass of the object, then it works. So you either have to have this rotation axis through the center of mass of an object, the equation then works, or it can't be a moving coordinate system. So that's what we're making use of. We're also going to make use of the fact, recall that A was equal to V minus V0 over T, and that tells us that alpha should be equal to omega minus omega 0 over T. So I'll make use of that as well. I'm going to do that part first. We're going to say 40.0 radians per second minus 0 radians per second divided by 4.00 seconds gives me 10.0 radians per second. So that's our alpha. That's the alpha that we're going to make use of. Now I'm going to go ahead and apply the Newton's second law for rotation. And the way I'm going to do that is I'm going to say the summation of the torques is equal to I times alpha. And what I'm doing is I'm going to assume that this is a positive torque. Okay. So in this case, you can notice that when a string comes off of a pulley, in general, the string always comes off perpendicular to a radial line, i.e. parallel to the edge of the pulley. And because of that, the torque, which is, let me give you another equation for that, torque is equal to R cross F. Since that's R times F times the sine of theta, when they're perpendicular like this, we see the theta is going to be 90 degrees, and therefore the sine of theta is going to be 1. So we don't even have to worry about the trig function. So that's what's going on here. And I've completely gotten rid of the vectorness of it by realizing that all this rotation is taking place in this in the plane of the screen. Yes, the torque pseudo vector sticks out of the screen and that sort of stuff, but that's okay. That can be represented by a plus or minus. So now that I've got that, I'm going to go ahead and say 15.0 newtons times 0.300 meters. That's the torque due to the force on the left-hand side. Minus, I've got the 1.22 Newton meters, which is the torque due to friction. And that's all got to be equal to I, which we're trying to solve for, times 10.0 radians per second every second. So we should be able to calculate that. If we take 15 and multiply it by 0.3, that's the same thing as 1.5 times 3. So that'd be 3 plus, that'd be 4.5. So I'm going to get 4.50 Newton meters minus 1.22 Newton meters is equal to I times 10.0 radians per second. So I is just going to be equal to, if I subtract 1.22 from 4.5, that'll be 3 point, once I subtract away the 0.2, that'll bring it down to 0.3, but then I got to take another 2, so that'll be a 0.28. So that should be 3.28 Newton meters divided by 10.0 radians per second. I'm going to double check my math. let's start off with 15 times 0.3. Yes, that's 4.5. I just want to make sure that was right. Now I'm going to take that 4.5 and subtract 1.22, and I get 3.28. That's right. And then I divide that by 10, and obviously that's 0.328. Notice the Newton is a kilogram meter per second squared. Okay, so when you're dividing by radians per second, that becomes a radian in the denominator and a second squared in the numerator. So the second squared is going to cancel out with this second squared, and I'm going to have kilogram meter squared, which is exactly the units we expect. So that is kilograms times meter squared is equal to I. So that's our answer. Now, in general, if you look at it, it looks like a cylinder. And if you've seen a pulley before, you'll notice that they have some cylinder-like characteristics. So it's probably not unreasonable to assume that it should be fairly close to a cylinder. So just as a check, let's calculate the moment of inertia for a cylinder. We know from the table it's 1/2 mr squared. So that's going to be 1/2 times 4.25 kilograms times 0.300 meters squared. So if I do 0.5 times 4.25 times 0.3 squared, that gives me 0.191 kilograms meter squared. That's not really very close. In fact, it's a good 50% larger. That's somewhat okay. I would not expect the moment of inertia of a cylinder of equal weight and equal radius to be larger, because generally a pulley will be made such that it usually has like a big bracket or some kind of U-trench at the outer edges that's a little bit heavier than the rest of the pulley, namely because the pulley's got to lie in there, and they usually keep some sort of railing or something like that. So if you think about it that way, then you would expect the moment of inertia of the pulley to be greater than the moment of inertia of a cylinder, and it's at least consistent with that. I was just surprised by it being roughly 50% larger. But anyway, either way, that's all good. Now, notice this one actually had a very specific case that we were solving. Specifically, this is a case in which someone is pulling down on this pulley with a force of 15 newtons, and that's a constant force. There's another way we can solve the same problem, but in this case, instead of it being 15 newtons pulling down on it, I'm going to put a 15 newton weight on it. And then that weight is going to be tempered, of course, by the actual tension in the rope. And of course, since the weight is in free fall, that's not a constant 15.0 newtons acting on it. So that brings me to the next problem. This was example 2. Anybody have any questions on this one before I move along? Okay. So this will be example 3. And again, I'm actually going to use the exact same information from this one. This radius is R, and this mass is M, which equals 4.25 kilograms, and this R is equal to 0.300 meters. We did find, for instance, that the moment of inertia was 0.328 kilogram meters squared. And we also used the fact that the torque due to the friction was equal to 1.22 Newton meters. Now, I did tell you guys it's probably best that you write newtons times meters. In other words, never, ever call that joules. But I also made a point to say it's probably best that you not do meters times Newton, because it might be easy to mistake it for a millinewton. And then I noticed that your textbook author does the exact same thing. He literally writes M times N. So I would still advise against that. It's just a little bit easier to make a mistake. Now, hanging from this will be a rope again, but this time we've got a 15.0 kilogram. Nope, excuse me. Got a 15.0. I'm going to go ahead and erase all this. What I'm going to do is say the weight of this guy is equal to 15.0 newtons. And since weight is equal to mg, that means this little m is about 1.53 kilograms. I'll double check that. 1.53 times 9.8 gives me 14.994. So yeah, that's the appropriate weight. So in this case, what I want to calculate is what is A and what is alpha. In other words, I want to calculate the angular acceleration as well as the linear acceleration of this. And I am going to assume the rope stays taut. I think that's the proper spelling of taut. And does not stretch. And moves without sliding on the pulley. In other words, when I pull down on that rope, say 1 centimeter, then what's going to happen is exactly 1 centimeter of rope that was originally touching the pulley is now going to no longer be touching the pulley, and the pulley is going to have moved such that a whole centimeter is moved. Okay, so that is sort of related to what we'll talk about in a few. When we actually let objects roll across the floor, we say they're rolling without slipping. That allows us to use a whole bevy of things. For instance, like, I'm going to write this here with the solution. For instance, like S the arc length is equal to r times theta. That literally means if you pulled out 1 centimeter of string, that would be your arc length s. If you then multiplied the radius times whatever angle that the pulley turned through at that time, you'd get that that's exactly equal to that same centimeter. Okay. Since that's true, we can take the derivative and get v equals r times omega. And since that's true, we can get a is equal to r times alpha. So that's really what's at work here. So first off, I'm going to draw a free body diagram for the weight. So the free body diagram has 1.53 kilogram mass. I'm again taking this direction to be positive and this direction, of course, to be positive as well. So what's going to happen here is I've got a force of 15.0 newtons pulling downward, and I got a tension in the string Ft pulling upward. So when I use Newton's second law of motion, the summation of the forces is equal to mass times acceleration. What I get is 15.0 newtons minus Ft is equal to 1.53 kilograms times A. That's going to be equation 1. Now I also have a Newton's second law for rotation. This has Ft here, this has R here, and now we can use the summation of the torques is equal to I times alpha. So again, in this case, the tension is going to, or the torque is going to be Ft times R. So I'm going to say 0.300 meters times Ft minus 1.22 Newton meters. And that is all equal to I, which is 0.328 kilograms meter squared times alpha. That's going to be equation 2. And then we're going to have A is equal to R times alpha, which says A is equal to 0.300 meters times alpha, and that's going to be equation 3. Any questions on those 3 equations? Okay. So now that we do that, we can, for instance, I could go ahead and solve equation 1 for Ft. So I'm going to now say Ft is actually equal to 15.0 newtons minus 1.53 times A. And I'm going to call this 1 prime. Notice I did leave off the units because it's getting kind of ugly. I'll actually leave off the newtons too in the next one. Now I'm going to plug 1 prime into 2. So 1 prime into 2. That's going to give me 0.300, leaving off the units, times 15.0 minus 1.53 times A minus 1.22 is equal to 0.328 times alpha. So we should sort of keep an eye on what's going on with the units, but other than that, we can still leave them off. Now I've got to distribute that 0.3, and the 0.3 times 15 should be 4.5. So that's going to give me 4.50. And notice that would then become newtons times meters. And the other thing would become a newton times a meter as well. So when I multiply 0.3 times 1.53, That's going to give me 0.459. So that's negative 0.459. Now that did have units. The 1.53 had units of just plain kilograms. Now I've multiplied that by a meter, so it's kilogram meter squared, or excuse me, kilogram meter times A. So that's really what the units are for the 0.459, but that's okay. And that was a 9-0, so I'm really am carrying an extra sig fig, just like the 4.50 was 4.500. That takes care of those first two terms. Now I've got minus 1.22. All that's equal to 0.328 alpha. So the problem is I've got an A and an alpha, and that means two unknowns. But if I substitute for A, if I substitute 0.300 times alpha, then I can have nothing but alpha there. So that's what I'm going to do here. I'm going to say plug in 3. Now that I do that, I'm going to say 4.50 minus 1.22. Now, in this case, I'm going to say minus 0.459 times 0.300 times alpha now, because R times alpha is A. So basically, I just made this equal to R times alpha, like that. So that's what I have down there. I've already moved the 1.22 over there, and the other side stays at 0.328 alpha. Okay, so 0.459 times 0.3 happens to be 1.377. 4.50 minus 1.22 gives me 3.28. So this is going to be 3.28 minus 0.1377 alpha, and the other part is equal to 0.328 alpha. So I can get the 3.28, which by now I think we can see is a Newton meter, because that's an actual torque. So that's a Newton meter. I'll put the unit back. Is equal to, now I'm going to take the 0.328 and I am going to add to it 0.1377. That looks like what I've done. And that's going to be 0.4657. That's one extra sig fig times alpha. So now I can say that alpha is in fact equal to 3.28 Newton meters over, now this 0.4657 should actually technically be a kilogram meter squared, which if you go back and trace it, you'll see that it is. And I'm going to do 3.28 divided by that 4.4657, and that's going to give me 7.043, and that's radians per second with one extra sig fig. And now we can compute A using equation 3. A is equal to R times alpha, which equals 0.300 meters times 7.043 radians, which remember is not really a unit at all, just a pure number. So if I take this 7.043 and multiply it by 0.3, that's going to give me 2.113. carrying 1 extra sig fig, and that is meters per second every second is equal to A. Any questions on that one? So notice how those two problems look very similar. They're the same pulley, the same friction, the same force in some sense. But in this case, it was actually a hanging mass. And because that's a hanging mass, the tension in the rope is not going to be equal to the weight that's hanging, because if it was, then the weight would just sit there and sit still. But the pulley is free to rotate. And since it's free to rotate, it's going to allow the mass to accelerate downward, so some of the force does not have to be supplied. And obviously from that, we got a much different acceleration. Before we had an acceleration of what, 10 meters per second 10 meters per second every second, or 10 radians per second every second. And this time we only got about 7.0 radians per second every second. Anybody have any questions on that? All right, so that's some fairly useful problems that are worthwhile working. Uh, there are other problems as well. For instance, your book does a heavy pulley. It also does a pulley in a bucket, which is sort of like the one I just did. Uh, all of those are good. A rotating rod is a good problem. I think this time I'm going to choose to work the rotating rod type problem. So let's start with this. This is going to be example 4. I'm going to ask again. Anybody have any questions? I feel like I'm just sort of steamrolling you guys, and I don't want to do that. Okay. So let's say a rod has a linear density of lambda is equal to k times, let's say, x squared. So that the integral of lambda dx is just equal to m. Okay. Compute the magnitude and units of k, and then compute I for the rod rotating about the x equals 0 end. And then let's call this part A. And let's call this part B. And then part C, calculate alpha and A of the end if the rod is hanged horizontally, and then released. Okay, so what I'm talking about here is you can imagine the rod looks like this, but given what I said, you might actually imagine the rod looks like this. And actually, I'm going to say the rod has a length L. So I'm going to put this along the x-axis like this. And I'm going to say this is a value L, that's a value M. That's my y-axis. And what I have to do is I am going to imagine that this has like a little pin in it so that it's free to rotate this way. That's what I'm doing for part C. Whereas for part A, I got to calculate the moment of inertia and all that good stuff. So first off, I know that I know that M, and I should really be writing this in a different color, so I'm going to erase that part. So solution. So M has got to equal the integral of lambda dx, which equals the k that's going to come out in front times the integral of x squared dx from x equals 0 to L. And of course, this gives me k L cubed over 3. That has to equal M. So from this part alone, I know that k is going to be equal to 3m over L cubed. So that's part of the problem. Also, the other part of the problem is we wanted to know the units of k. So you can see from here that the units of k would be kilograms per meter cubed. So that's another answer as well. Yep. Any questions on that part? All right, now I've got to calculate the moment of inertia, because what I'm trying to do is everybody sees the rod with that little pin in the left-hand side. That little pin in the left-hand side right there, that is supposed to be like the axle. So this thing is hanging horizontally like this, and it can just fall as a result of its own weight. But in order to do that, I got to figure out where the center of mass is, and then I've got to figure out what the moment of inertia is about that end. So first off, I got to calculate the center of mass. So I'm going to do part B here. X center of mass is equal to the integral of x dm over the integral of dm. The integral of x dm, of course, is going to become the integral of, now remember we have k x squared for lambda, then I have an x that's already there, and then a dx there, and I'm going to integrate from 0 to L. Meanwhile, this part's just going to be plain m. We've already worked that out. So this is going to become k times the integral from 0 to L of x cubed dx over m. We know that k is 3m over L cubed. So I'll put that there. The m on the bottom is already there. And now the integral of x cubed from 0 to L is 1/4 x to the 4th. So that's going to be 1/4 L to the 4th, like this. So we can see that this 4 completely cancels out with those L cubes. The m's cancel out with the m's. And ultimately, I am left with the center of mass is equal to 3/4 L. Okay. So if I go all the way over to here, that's the center of mass. And if I want to see how this thing's going to behave when gravity pulls it down, then that means there's going to be a force right here of mg, and that distance from here to here is 3/4 L. Okay. So I now have the center of mass of that rod, and I'm just going to allow it to fall under that force. And I only care about that split instant that it's released, because the acceleration is not going to be a function, is not going to be a constant. It's going to probably change a little bit. So if that were the case, then just answering it for the time t equals 0 is sufficient. So let me go ahead now and calculate the moment of inertia. So I is equal to the integral of r squared dm. The r in this case is really just x, so it's going to be the integral of x squared, and then the dm is just going to be lambda dx, but lambda is k times x squared. So I'm going to get k integral x to the fourth dx from x equals 0 to L. And that all looks pretty good to me. So this is going to be k over 5 L to the fifth. Now I've got to put in what k is. So I'm going to say 1/5. And then k was 3m over L cubed. And then that's times L to the fifth. What I can see is this 5 will cancel out all three of these and leave just a 2 there. And I'm going to get that the moment of inertia is 3/5 ml squared. Okay. So that was another thing we had to compute. So I is equal to 3/5 ml squared. And now we're ready for part C. So for part C, just reminding us what we have here, I'm going to draw this rod again. And really, to make the rod sort of look real based on what its density is like, it should sort of be going like y equals x squared like this. That would be a way to represent what the weight is like. Just imagining that it's getting heavier and heavier farther you go to the left. I'm going to say this right here is at L, and then of course this right here is 3/4 L, and right here I have a force mg acting on it, and like I said, it's free to rotate about that position. So I'll say the summation of the torques is equal to I times alpha. In this case, the only torque we have really is the weight acting on it, and that is force times lever arm. Notice that with it being horizontal, the force is perpendicular to that, it's vertical. Therefore, it's just the lever arm times the force. So in this case, I'm going to say 3/4. Actually, let me go back to purple. It's going to be 3/4 L, that's your lever arm, times M times G, that's the force. Of course, the sine of 90 be 1. That's all got to equal. Now I've got to put in I, which is 3/4 ml squared times alpha. So at this point, you can see that the M's do cancel out, and you can see in fact that one of the L's cancels out, as well as the 3 canceling out. And what I get is alpha is equal to 5/4 G over L. So that's the angular acceleration. And of course, A is equal to R times alpha. In this case, we're actually wanting to know how fast the end is going. So I really want to know A right here. So the R has to be the actual L. So A for the end, and actually I don't know why I'm still writing in blue. Let me change it to purple. So A for the end is going to equal L times alpha, which is of course L times 5/4 G over L. And you can see that the L's cancel out, and this thing is actually going to fall at A equals 5/4 G. Notice that is faster than gravitational acceleration. I was telling my students today that if you ever see like a smokestack or a silo fall, a lot of times you'll see them break in the middle of the fall. The reason why is normally you have to build them to withstand winds that really don't do any more than maybe 1 times gravitational force. So they're expected to accelerate up to G. But in this case, since it's accelerating faster than G, it hasn't been designed structurally to stand up to that kind of stress, so it breaks. And the reason why it breaks is because the center of mass acts where all the force is acting. So when the gravity is starting to pull down on the object, it's acting at that center of mass, which for a regular smokestack would be L over 2. But the end of it's going twice as fast as that, and the center of mass is going to fall at G, 9.8 meters per second, whereas the end's going to fall at 2G. So somewhere between the middle and the end, if it's designed to handle 1G, somewhere in between the middle and the end, it's going to crack. Anybody have any questions on this? Now that problem was a lot more involved than the one your book does. Your book does a simpler one, but I think with all the work we've done so far, I think you can pretty much figure out how to do the simpler stuff, and it's just a matter of then to add the different steps. But notice the problem here was really we had a rod whose density was not uniform. This is a non-uniform mass per unit length rod. In fact, what we found was the mass per unit length was proportional to the square of the distance away. So it actually got much, much heavier the further you got to the right end from the left end. And because of that, we had to first figure out what the center of mass is, because, well, other than doing the calculation to figure out K, but we had to do a center of mass calculation to find out where gravity was going to act as if it's doing all the force at that particular location. And from that, we found 3/4 L. Then when we did that, we had to find the moment of inertia because it's going to rotate about that end. And that's why I did integral of r squared dm. That gave us 3/5 ml squared. And then I was actually able to solve the problem. And of course, that's just actually, if I'm looking at it now, oh yeah. So the problem with this torque equals I times alpha, it's exactly correct at t equals 0, but notice alpha, as the arm starts to fall down, the angle that gravity makes with the lever arm changes. So you're actually going to get a sine theta in there, and that's just a nightmare. So that's why I only wanted to calculate the acceleration at the instant. So let's remind ourselves, these A and alpha are only true at t equals 0. Okay. Anybody have any questions? All right. Well, we worked a little bit of the parallel axis theorem. I told you we're completely skipping the perpendicular axis theorem. Good for you to know and good for you to read about. So I highly recommend you reading those sections, but I'm not going to test you on them. What we do need to know, though, is what happens to energy. So, for instance, our next example is 5, but for instance, in conservation of energy, let's refresh ourselves on that. So what I recommended you guys using for conservation of energy was work in plus potential energy initial plus kinetic energy initial is equal to work out plus potential energy final plus kinetic energy final plus E loss. Well, what's going on now? Remember, we're trying to go from solving physics problems where I'm dealing with point objects, in other words, little particles that have no physical dimension or have a very small physical dimension compared to the distances and stuff they're moving about their center of mass. And what we've discovered is there's F equals ma or F equals dp dt that applies to the center of mass, and we can use that all day long. But that just tells us how the center of mass is going to move. If we want to know really what is it going to do, like through what angles it's going to turn and all sorts of stuff like that, what way is it going to be oriented when we actually hit the ground or something like that, then you've got to have another equation for the torque about the center of mass, or if you can muster it about any axis, as long as it's meets the criteria of a inertial reference system and attached to the object. But the main thing is those two in combination can tell us how a whole body moves. So when we do that, what we need is not only the kinetic energy of the center of mass, the 1/2 mv squared, we also need a 1/2 I omega squared. So the only thing we have to do here is we've got to add another term in here. So instead of this just being 1/2 mv final squared, it's going to be 1/2 mv final squared plus 1/2 I omega final squared. And the same thing here. This is going to be 1/2 mv initial squared plus 1/2 I omega initial squared. And the moment, the 1/2 mv squared has to be the kinetic energy of the center of mass. Okay. So like that. So with that in mind, let's try solving a specific problem. So this is going to be example 5. What I would like to do is I'm going to have an inclined plane of height h and angle theta, and I'd like to know v final equals question mark a for a sphere of mass m, radius r, and this is rolling without slipping. And then B, I would like to do a hoop of mass m and radius r, and C, I would like to do a cylinder, mass m, radius r, v final, question mark, rolling without slipping. And then finally D, a hoop sliding, without friction. Okay. So here's our solution. Now I will make use of some facts that I know. I know, for instance, the moment of inertia of a sphere is equal to 2/5 mr squared. The moment of inertia of a hoop is equal to mr squared, and the moment of inertia of a cylinder is equal to 1/2 mr squared, like that. And I'm also going to make use of work in plus U initial plus K initial equals work out plus U final plus K final plus E loss. Now, in this case, basically, there is going to be some energy loss to friction, but I'm going to assume that's kind of small. And in fact, we're going to assume that the work out, the work in, the energy loss are all zero. So I'm just going to write this up here and say 0, 0, 0. Not only that, I'm going to assume this height has U equals 0. So the initial potential energy, excuse me, the initial kinetic energy is going to be 0, but the final potential energy is going to be 0. So notice I've made a lot of simplifications already. Now we can start up with part A, which is supposed to be a sphere. So I'm going to say M times G times H. That's how high the object's going to be, is H. So the potential energy is M times G times H. And then that is equal to the final kinetic energy, which is 1/2 mv final squared plus 1/2. Remember, it's I omega squared, but this is for a sphere, so it's going to be 2/5 mr squared times omega final squared, like this. And then if I use the fact that it rolls without slipping, then I can also use the fact that V final is equal to R times omega final. So I can now say MGH is equal to 1/2 mr squared omega final squared, because V is equal to R omega, plus 1/5 mr squared omega final squared. And of course, 1/5 plus 1/2 would be 5/10 plus 2/10 equals 7/10. So this would be 7/10 mr squared omega final squared. Now we can look and see that the m clearly cancels out on that case, and we can solve for omega final is equal to 10 GH over 7. Now I'm going to take the square root of that and then divide it by R, because technically I'm taking the R squared, which would be in the bottom, and when I take the square root of that, it just becomes R in the bottom. So that's going to be the actual speed. We can say that's the angular speed. We could also write it as 10 GH over 7R squared. Notice that's completely independent of the mass. That's one of the key things we're learning here, but it does depend on the radius. Now we can also say that V final is equal to R times omega final. So I can just get rid of that and say that's going to be the square root of 10 GH over 7. That's the velocity of the sphere. Notice I did make all the shapes all the same mass and radius, so that shouldn't come into play. If I do part B, you can see basically what happens is I get the M, the G, the H. That's equal to 1/2 mr squared omega final squared plus now for the hoop, it's just mr squared. So that's going to be 1/2 mr squared omega final squared, and a half plus a half is 1. So this equals just mr squared omega final squared. And you can see again that the mass cancels out. And we get that omega final is just going to be equal to the square root of gh over r squared. And then v final is going to be the square root of just plain gh. So this is for the hoop. Notice the hoop is going a little bit slower, right? It's the difference of the square root of 10 over 7. So let's see what that is. Square root 10 divided by 7. That's about 1.19, about 1.19 times slower. So the hoop definitely goes slower. When we do the cylinder, it's going to be essentially the same thing. So I can say C. Ooh, I'm going to try to fit it in here in this one little space. So here's C. What I'm going to do is say mgh. Now I'm going to have 1/2 mr squared omega f squared plus 1/4. So this is going to be 3/4 mr squared omega final squared. Again, we can see the omegas, or excuse me, the m's cancel out. But this time we're going to get omega final is equal to the square root of 4gh over 3r squared, and v final is just equal to the square root of 4gh over 3. And that's for the cylinder. If we were to do the hoop sliding without friction, that's just going to be m times g times h equals 1/2. In this case, it's just m times v final squared, because it's not rotating, it's just sliding. So in this case, you can see the m's clearly cancel out, and we get v final equals the square root of 2gh, which is clearly faster than any of them. So notice the moments of inertia are like mr squared, and then you've got factors like 2/5 that make it a little smaller so that the sphere can go a little faster than the hoop. And then you got a factor like 1/2 for the cylinder. That means the cylinder can go even faster than the sphere, and so on and so forth. So that's where all that comes in. Anybody have any questions on that? All right. What I'd like to do now is I'm going to solve a problem for us to calculate what's the actual friction required for something to roll without slipping. And we're going to do it with just your traditional Newton's laws of motion. We've sort of handled just about everything that your book handles in chapter 10 anyways. But here goes. This is example 6. So again, I'm going to imagine a sphere. In this case, it's just a sphere. And I'm going to say its radius is r and its mass is m. And I'm going to say that it rolls down an incline without slipping. find A, alpha, and the friction force. Okay, that's what we're wanting to find. I'm going to say that this height right here is just H, and that this, well, that's good enough actually. Okay, so that's our actual picture. Now, what I'm going to do is draw my coordinate system inclined. And I actually wanted a different color other than blue, but I guess we're going to get blue. Okay. There's my y-axis. Now, what I'm picturing here is my sphere like that. Okay. Now, it has acting on it right at its center of mass is its weight acting. And that's just plain m times g. Of course, we know this angle is theta, which means that this angle right here is 90 minus theta. And of course, this angle all the way around is actual 90. So that has to be theta there, which means we can now say this particular component of the weight is mg cosine theta. And this component is mg sine theta. Now, we also have a normal force, which notice I drew it right on the center of mass. In principle, it actually comes from the bottom, but it goes right through the center of mass. That's our normal force. The reason why I'm saying that about the weight mg and the normal force Fn is because they literally have no torque that they can apply because they applied directly to the center of mass, and the center of mass is about which we're rotating, so the lever arm is 0. So I'm going to say, write this here, lever arm equals 0 and lever arm equals 0. Okay. Now, in order for it to actually roll without slipping, we also have to have a friction force, which is going to act right here. And I'm just going to put a script F like that to show the friction force. So first thing I'm going to do is summation of the forces in the y direction equals mass times acceleration in the y direction. But of course, the acceleration in the y direction would be like it's bouncing up and down the incline. So that's going to be 0. So in this case, I just get F normal minus mg cosine theta is equal to 0. And that just tells us that the normal force, as expected, is mg cosine theta. Now I'll do the summation of the forces in the x direction equals mass times acceleration in the x direction. In this case, we're actually going to have the force acting down the incline is that's actually about positive direction. So I'm going to say mg sine theta minus my friction force, and that's got to equal m times a. So this is going to be equation 2. Everybody follow what we did so far? Now, in this case, I'm not free to just choose any axis like I can do with a lot of problems. In this case, the actual ball is rolling down the incline, and that's an accelerating reference frame. So I can only apply this to an axis going through the center of mass. So I'm now going to say the summation of the torques through the center of mass is equal to I through the center of mass times alpha. Now, you can see, since I said Fn has no lever arm and mg has no lever arm, then that means mg cosine theta, mg sine theta, and Fn are not contributing to the torque whatsoever, but the friction force is. So in this case, I'm going to say R times F, because they're perpendicular to each other. And notice that the friction force is applied at the end of the diameter, which is a distance r from the center of mass. That r times F is equal to 2/5 mr squared times alpha. In other words, 2/5 mr squared is just the I for the sphere. That's going to be equation 3. So from this alone, we can already see that this r squared drops out and leaves no r over there. And I've got F is just 2/5 mr alpha. So if I can figure out what alpha is, then I can have a way to figure out what the friction force is as well. Not only that, r times alpha is A. So what I have right now, I can call this 3 prime, and it basically says F is equal to 2/5 m times A. So that could come in handy as well. If I plug that back into equation 2, so 3 prime into 2, then I get mg sine theta minus 2/5 ma is equal to ma. Then I can pull the 2/5 to the right hand side. That'll be 2/5 plus 5/5. And of course, 2/5 plus 5/5 is 7/5. So now I can say mg sine theta is equal to 7/5 ma. You can see the m's cancel out beautifully. And we now have A is equal to 5/7 g sine theta. And that's all in terms of stuff we know. The theta, for instance, we're assuming we're given. We can also use the fact that A is equal to R times alpha to tell us that alpha is equal to A over R. So alpha is equal to A over R gets us basically 5/7 g sine theta over R is my alpha. So that's another one we had to solve. And then finally, my friction force. Now that I know what my acceleration is, my friction force. Sorry, I keep switching back and forth between the wrong colors. So my friction force we found was 2/5 ma. Well, that's 2/5 m times 5/7 g sine theta. So it turns out that the friction force is just 2/7 mg sine theta. That's it. Anybody have any questions on that one? If you look at problem from your book 1019, that's essentially the same problem. I used different symbols. Actually, we even both used a sphere. So they got a friction force was equal to 2/7 mg sine theta. I got the same thing. They got the acceleration was 5/7 g sine theta. That's the same thing I got. And then of course, if you divide that by r, that's alpha. So we got all that. So you guys are free to go. I'll wait for the last person to leave in case anybody has any questions. But other than that, you're free to go. Don't forget to chat me your first and last name. I know someone just left just before I said that. That's a bummer, but
Thank you. Have a good one.
you're welcome. You too. Did anybody see who it was that left? Because I got to type their name in to save them in a little bit of trouble. Maybe they'll log back in a second when I remember. Anybody have any questions? Those. That's it. No one else? All right, we're finished with chapter 10 anyway, so I'm not sure Jonathan or Hannah's still here, but I did type their names in just in case. And I'm going to stop sharing my screen now. It looks like everybody's. Nope, they're still here. All right, well, they don't seem to be asking me any questions, so I'm not sure they're even there in reality. So I'm going to go ahead and kill it. Bye, everybody.